Let me discuss based on the question what we discussed last time. Suppose if you have been given something like this, where you have 9.8 grams of H3PO4, you need to figure out what are the number of moles of H3PO4, what are the moles of oxygen, what are the total moles of atoms. Okay. In such case, what you can do, check it out. Moles of H3PO4 will be simply the mass divided by the molar mass, which is 98. So 0.1 moles. 0.1 moles can be also written as 0.1 Na molecules. Similarly, if you want to check out how many oxygens we have, see, every 1 mole has 4 moles of oxygen. So therefore, number of moles of oxygen atoms is equal to 4 times number of moles of H3PO4, which makes it 0.4 moles. Likewise, if I have to calculate total number of moles, so total number of moles of atoms, it will be, see how many we have, 4 plus 1 5, 5 plus 3 8, so 8 times of number of moles of H3PO4, which makes it 0.8 moles. That's how they are related to each other. Okay, beta?
Yes, sir.
Next, if the question is given like this, where you have been given find the mass of neon gas if it contains 8 Na electrons, find the volume of neon gas at 1 atm as well. Okay, so atomic mass number is given as 20. Mass number is 20. So you know that number of protons will be same as number of electrons, which means there are total of 10 electrons. So one molecule has 10 electrons. So if you have 8 Na electrons, correct? So let me put it this way. 10 electrons signifies to, one atom of neon, which means if at all I have 8 Na, that will signifies to how many number of atoms. So number of atoms of neon will be equal to 8 divided by 10 into Na. So which is
8 Na.
0.8 Na. These are the number of atoms. If you know the number of atoms, how will you get number of moles? Number of moles will be equal to total number of atoms divided by Avogadro's number. So which is 0.8 moles. So these are 0.8 moles we have. Based on moles, we can calculate what is the mass of neon. So mass of neon will be equal to 0.8 into atomic number mass number. So how much we will get? 16 grams is what it is. And what will be the volume? Volume of neon gas will be equal to total number of moles, which is 0.8 into 22.4. If at all you are taking it at 180 and 273, it is at NTP condition. Okay, beta. So that's what we need to check it out. I suppose this question is clear.
Yes, sir.
To 0.8. That comes to be 17.92 liters. Next. If you have been asked to figure out which has maximum number of atoms in this given cases. So notice we'll start with first case. First case we have 2.2 grams of carbon dioxide. So number of carbon dioxide is 2.2 by 44. So that makes it 0.05. Correct? These many moles we have. So number of atoms, how many we have? Number of atoms will be 0.05 into 3. So which is 0.15 moles. Next, if you compare B, number of moles of SO3 will be 0.224 divided by 22.4, which makes it 0.01 moles, which is number of atoms in this case will be equal to 4 times of it, 0.01 into 4. So 0.04 moles. Next, if you notice, number of moles of H2CO3 will be equal to 0.Na by Na, so which makes it 0.1 moles. So number of atoms present in it will be equal to, so total you can see 6 atoms are there in H2CO3. So 6 into 0.1, which makes it 0.6 moles. Next, if you have D, you have 2 gram atoms of helium, so which means number of moles of helium itself is equal to 2 moles. So number of atoms is 2 moles. Next, E, 125 units of H2 gas. Okay, and you know that one unit, one unified mass is equal to how many? 1.66 into 10 raised to the power of 28, or this divided by Na is the number of moles, correct? So number of moles of H2 gas will be equal to 128 divided by 2 Na. Okay, sorry, only Na. This many number of moles. So number of atoms will be equal to 2 times of 128 divided by Na. These are the number of atoms. If you compare 18 ml of, this is in moles by the way, 18 ml of water, 18 ml of water means number of moles of water will be equal to, mass and volume will be same, so 18 by 18, that makes it 1 mole. Clear beta? So out of all of this, which has the highest value here? Helium. That's typical way of solving these kind of questions. Now, today our emphasis is more to do with the stoichiometry. Got it? The stoichiometry is basically relates to the calculation of chemical compounds. What do we calculate? Mass, moles, volume, these kind of stuff. This calculation is based on balanced chemical equations. And within these balanced chemical equations, we always follow conservation of mass principle. Okay. So given any chemical equation like this, you should be able to balance it in the first place. Got it? So you can see there is a nitrogen here, there is nitrogen here. So whichever is a bigger number, you try to balance that first. So what you can do to make it more even, to put 2 here and 3 here. And now you can see nitrogen is also balanced that way. Okay. If all 3 are gases here, so we can always read it in terms of moles. That is 1 mole of, this is called reading the equation. 1 mole of N2 reacts with 3 moles of H2 to form 2 moles of NH3. This is called reading the reaction. Okay, beta. Next, if you have KClO3 giving like this, so again, if you try to balance it, there are 2 potassiums and 3 oxygens, which makes it, I should have 2 here to balance it. Now it is balanced. So how do we read it? 2 moles of KClO3, okay, decomposes to form 2 moles of KCl and 3 moles of O2. Yeah, good. Next, in case if the values are not given and you are supposed to figure out what are the values, okay, so you can use simple algebraic equations first and then you can read the reaction as well. For example, if you notice in here, you can see the chlorine is present here as well as here. So which means whatever be the 2 times of A atoms of chlorine we have, that should balance C plus D. This is one equation I can get. Okay, beta. Next, if you compare potassium, you can see B moles of potassium or B atoms of potassium should be balanced with C plus D, correct? Which implies 2A is equal to B. This is one thing we got. Hmm? And if you compare the hydrogen here, correct? Oxygen here, oxygen says 2B moles will be equal to 3D plus E. This is another way of balancing it. And then B will be equal to 2E. This is another way of balancing it. Okay. Now you can assume any one value and then calculate the rest. And thereafter you can multiply any common value to get the simple integers. For example, what I can do, I can take A is equal to 1. So I'll get C plus D is equal to 2. And B will be equal to half. Okay. Sorry. B will be equal to 2. Okay. If A is equal to 1. And if B equal to 2, E is equal to 1. Correct. And C plus D is equal to 2. And you can see here E is equal to 1, which makes it 3D is equal to 2 minus 1, which is 1. So D is equal to 1 by 3. Okay. And if D is equal to 1 by 3, what will be the value of C beta? C will be equal to 2 minus 1 by 3, which makes it 5 by 3. Correct?
Yes, sir.
Now, let me put all of these values here back into the equation. So if I take that here, let me remove all of this and put that values. So A, I took it as 1. B, I got it as 2. C, I got it as 5 by 3. D, I got it as 1 by 3. E, I got it as E, how much we got? 1. Okay. The common factor I can multiply to make it simple integer is 3. So after multiplying with 3, I will get this as 3 Cl2 plus 6 KOH is giving 5 KCl plus 1 KClO3 plus 6, sorry, 3 plus 3 H2O. So I'm sure now you know how to read the reaction here. So we can say, right, 3 moles of chlorine in 6 moles of base. I'm using the word base instead of KOH because it's a base. In 6 moles of base forms 5 moles of KCl, 1 mole of KClO3, and 3 moles of H2O. Okay, beta. This is the way we can put it. Clear?
Yes, sir.
Next. Lastly, if at all I have I2, in a similar way, if you balance it, correct? What is the value you will get here is 10. And here you will get 2. And here you will get, sorry, I will have another one, 10 NO2. And then I'll have 4 H2O. This is the balanced form. Now you know how to read the reaction as well, correct? Right. Now, what is the significance of balanced equation? Let's see. Significance of balanced equation. Okay. The numbers which we use to balance it, they are called, okay, the numbers used for balancing, numbers used for balancing, they are called stoichiometric coefficients. They're called stoichiometric coefficients. Got it?
Yes, sir.
Yeah. Correct. So these will be in the ratio of moles or molecules. You can read it as moles or molecules. Okay. these numbers are in the ratio of moles or molecules and volumes in case of gases. You can use this as volume terms also, like A volume, B volume, C volume, like that. Okay, correct. Now, for example, if I pull the same thing here, how we have read the equation, I'll just show you that idea here. For example, if you consider this same thing, N2 plus 3H2 giving 2NH3. This is the preparation method of ammonia known as Born-Haber process. Okay, beta. Now, in this case, since all of them are gases, I can use it this way, that one volume of N2 reacts with
B1.
3 volumes of H2 to form 2 volumes of NH3. Got it? If you are able to use this, we simply call it as Avogadro's law. This is following Avogadro's law. Okay. Now you might read in the other way also. What if I have for this equation, when I'm using this one, what is the basic assumption is assuming pressure and temperature of system is constant. Got it? This is the assumption. Similarly, if at all I have to read in terms of pressures, I can do that also. Like, let's say I can use it as 1 atm with 3 atm giving 2 atm. In that case, I am considering volume and temperature are constant. Clear, beta? Volume and temperature are constant. All good?
Yes, sir.
Right. See, when it comes to chemical reactions as such, you have many type of reactions. Okay? We do have many type of reactions. Let me get into that part now. Types of reactions. The first type, which is most probably asked for, NSCJS, that majority of the questions, if you notice from the previous year from mole concept, they're mostly related to these kind. That is decomposition reactions. Got it? Specifically, the decomposition which it will be asked to you will be carbonates and nitrates. Okay, but I have hardly saw any question on nitrates, but definitely carbonates. Okay, so first type we will see is carbonates. Okay, so when it comes to carbonates, we have two types of carbonates which decompose. One is alkali metal carbonates. Got it? Alkali metal carbonates. So which means alkali means, first group element which will only have plus charge on them, and carbonate implies CO3 2 minus. Got it? To get the neutral form of a molecule, you have to cross multiply their charges. So what do I get? M2CO3. This is the existence of alkali metal carbonates, correct? Now if you have M2CO3 solid, if you try to decompose, and it will become M2O solid plus CO2 gas. Here it is only observed with lithium. Got it? While if you notice M2CO3 solid making no reaction on heating, that means all other metals, sodium, potassium, rubidium, cesium, these metals do not decompose in their carbonates. Clear? While on the other hand, if you take, alkaline metal carbonates, if we consider alkaline metal carbonates, that means metal will have plus 2 charge, carbonate will have 2 minus charge. So that makes it MCO3. And MCO3, usually when you take and heat it strongly, it will become MO solid plus CO2 gas. Here all metals decompose: beryllium, magnesium, calcium, strontium, and barium. So have you noticed something in the entire periodic table? It is only the group 1 carbonates which are stable on heating. Otherwise, rest of the group elements, any other group elements, they will only decompose their carbonates.
Sir,
So carbonates is clear, beta?
yes, sir. Sir, what is the difference between alkali metal and alkaline metal?
Right. When it comes to alkali, that means it is directly basic. Okay. And these metals are usually, when you use these metals and directly add it to water, they will convert into a basic solution. Like sodium, when you add it to water, it will become NaOH. Potassium will become KOH, and so on. That's why they are called alkali metals. While when it comes to alkaline metals or alkaline earth metals, they also show alkalinity, but they are often identified in the earth crust only. Right? That's why they are categorized as alkaline earth metals. But the idea is the same. As you add it to water, they will also become hydroxides, which are basic. Okay. Next. The second type, if you notice, this is about bicarbonates. Bicarbonates. When you use the word bi, that means you have one hydrogen on it. Okay. So in case if you talk about alkali metal bicarbonates, then you'll have M plus and HCO3 minus. And alkaline metals showing bicarbonate means M2 plus and HCO3 minus. The compound which will form here is MCO3, MHCO3, and here what it forms is MHCO3 twice. Correct. Now, if we compare these two bicarbonates, in fact, any bicarbonate in general, right, will always decompose. So if I take 2 moles of it, it will decompose into formation of M2CO3 solid plus H2O, right? It could be gas or liquid depending on the temperature, but this is what is the decomposition looks like. While if you take metal bicarbonate here, as you start heating, this will convert into metal oxide plus 2 moles of CO2 plus 2 moles of H2. Huh? So this is the major difference between alkali metals, how they decompose in their bicarbonate forms, and alkali earth metals, how they decompose. Clear, beta?
Sir.
Next. Type 3, or I will say C, is about uh, decomposition of gases. Decomposition of gases themselves. Again, you would be typically used to check out these kind of gases. NXHY gas, that on heating usually becomes N2 gas plus H2 gas, which clearly shows that it should be Y by 2 here and X by 2 here. Then, similarly, if you have PCl5 gas, it will decompose into PCl3 gas plus Cl2 gas. Next, N2O4 gas decomposes on heating to become 2NO2 gas. Okay. Next, if you have any O3 gas, it will decompose to convert into O2 gas immediately. So if I take 2 here, it should become 3 here. Okay, right? Another gas which you will might be commonly asked is SO3 gas, that on heating will convert into SO2 gas and half of O2 gas. So these are all gas decompositions. Usually, gas decompositions always happen as you heat them. Okay, on heating, they will all convert into this other gaseous forms. So, is the decomposition part clear, beta? These are
Yes.
the decomposition reactions which you should be aware of. Second type of reactions include combustion reactions. Combustion reactions. This is burning in excess of oxygen, gas. Got it? Any carbon material you have, it will convert into carbon dioxide. Sulfur will convert into sulfur dioxide. Nitrogen will not convert into anything. It will remain as N2 only. That means I'll put it as N2. So no conversion here. And hydrogen will convert into H2O. Carbon monoxide gas will also convert into carbon dioxide. All this idea is clear, beta? Right. Now, generally, most of these reactions are operated at room temperature or just above the room temperature. For example, if you have hydrocarbon, this is most asked case, CXHY. If you have CXHY as a gas, that when you react with O2 gas, the carbon part is expected to convert into CO2, plus hydrogen part is converted into H2O. Because it is at room temperature, most of the time you have to write water in liquid state, unless it is clearly specified in the question that you are operating at a temperature above 100 degrees Celsius. Okay, and next, how do we balance it here? You can clearly notice that 1 mole of CXHY gas plus, the way to balance is always first balance the carbon here. Got it? So as you balance carbon, you should get X moles of carbon dioxide plus, Y by 2 moles of H2O liquid, correct? And on the left hand side, because you have to balance oxygen, this is 2X plus Y by 2. So I will write this as X plus Y by 4. I'll write this as X plus Y by 4 times of O2 gas, correct? That will be times of O2 gas. Now you can see the oxygen is also balanced, isn't it? Is that okay, beta?
Yes, sir.
So this is how you can balance the oxygen part. This is when you have hydrocarbons alone. What if I give you another example where you have CXHY and OZ also present? In that case, the idea is still the simple one, CXH plus and OZ plus. As you balance, you will get this as X plus Y by 4, that is evident. And then you have to separate this by Z by 2, isn't it? That of O2, rest is the same. So you will get here as how many moles? X moles of CO2 gas plus Y by 2 moles of H2O liquid. Done. What if I have CXHY and NZ? If you have NZ, you know that CHXY plus X plus Y by 4 times of O2 gas that will decompose to form, or combustion undergoes to form, X moles of CO2 plus Y by 2 moles of H2O liquid plus N2. How many moles here? Z by 2 moles of N2 gas, because N2 is not the one which will convert into oxide.
Yes, sir.
All good, beta?
Yes, sir.
Right. Now, whenever it comes to, I mean, you got an idea about what are the types of reactions we will be mostly dealing with. At the same time, given any decomposition reactions, right, you should be able to relate with the reactants to products, any product, and based on that product information, you can guess whatever the question is. So let us see the problem solving type, first one. Problem type 1. The first type is being, let me take this example. I have calcium carbonate, which on decomposition will convert into calcium oxide plus carbon dioxide gas. Okay. Given is 50 grams of carbon dioxide, and we need to find out what is the volume of carbon dioxide at NTP. This is one type. Okay. So here the logic is simple. Always try to relate with number of moles. Check out, it is 50 divided by molar mass is 100, which makes it 0.5 moles. As a balancing part, it is already balanced 1:1 ratio. So therefore, number of moles of carbon dioxide that are formed is 0.5 moles, which means volume of carbon dioxide will be 0.5 into 22.4 liters, which is 11.2 liters of carbon dioxide is released. The type 1 is clear.
Yes, sir.
Okay. Next, the same question can be asked, saying that in an open vessel, in an open vessel, clear, how much how much mass is remaining, how much mass is remaining when, you know 200 grams of calcium carbonate is decomposed. If this is decomposed, how much mass has been formed here? So that means you will take calcium carbonate, you heat it strongly, it will become calcium oxide plus CO2. So now the weight is 200 grams, which means number of moles is 200 by 100, which makes it 2 moles. Since this is 2 moles, you know that carbon dioxide escapes into the atmosphere. So what is left is only calcium oxide. So these 2 moles will form number of moles here as 2 moles. So what is the weight of calcium oxide? That will be, this is 56 multiplied by 2. 56 is the atomic molar mass here. So how much we are getting? 112 grams. So we got how much gas, how much mass has escaped? 200 minus 112, which is 88. 88 grams has escaped and 112 grams is left. Clear, beta?
Yes, sir.
Right. On a similar lines, if the question is framed like this, you know that uh, 1 mole of sodium bicarbonate decomposes decomposes hmm, at high temperature. Find the mass of residue left. These kind of questions are asked. Then how do we solve it? You can take this as sodium bicarbonate, take 2 moles, heat it, you will get Na2CO3 solid. This will be solid, and you will get CO2 gas, and H2O also you take it as gas. Why? He specifically mentioned it as high temperature. Hmm? So that is also lost. So we have 1 mole of Na2SO4, that is before heating, and as you heat you will get this product. So 1 mole implies 1 mole of Na2CO3 form. So 1 mole here is how much? 84 grams, correct? Sorry, this is half mole. So 0.5 mole, isn't it? Because you see the ratio, 2
Yes.
moles is equivalent to 1 mole. So 1 mole will give you half mole. Yeah. So it was 84 grams. Now, how much will be left here? So weight of Na2CO3 left will be equal to 0.5 into molar mass, which is 106. Clear, beta? So how much do we have? 53 grams. So 53 grams is left over and 31 grams is released part. Okay. Yoshi, clear, beta?
Yes, sir.
Right. Okay. One second.